Alright, so in this segment we are going to talk about the structure of the files. Okay, so the files that we're storing the records, it can be ordered, unordered, or hashed file. So let's see what if the file is an unordered file. So unordered file is also known as heap file. So the mean is that when we're going to store a record. All right, so the records in that file will be in any order. Okay, it is not going to be ordered, so it is going to be unordered. So in that case, when we will insert a new record, insertion is actually easy and straightforward, because we are going to insert a new record at the end of the file. All right, so in the unordered file, how to search a specific record in that file. So the only searching we can implement is linear search. Okay, means a linear search is going to search every records in that file. Okay, every record in that file to search for a record. So this is going to require like reading and searching. On average, it is going to require half of the file blocks on average. Okay, so it's quite expensive. Record insertion is efficient because actually we are going to insert the record, a new record, at the end of the file. Okay, so the reading the record in order of a particular field is going to require sorting the file record. So if we have a unordered files, but we want to read the record in a particular order, in that case what we have to do, we have to first sort the record from the file, and then we have to read them, right? Now the file can be also ordered file, also known as sequential file. So in the ordered files, records will be stored as a ordered on a particular attribute. Okay, so file records are kept sorted by the values of an ordering field. So in the ordered file, insertion is expensive because when we will insert a new record, it has to be inserted in the correct order. Okay, so sometimes actually it's common to keep a like separate unordered overflow for a new record to improve the insertion efficiency. Okay, it means actually you are going to just insert a record, all right, and then periodically you are going to merge them with the main ordered file. Now searching in the ordered file is efficient because here we can implement binary search. Okay, so a binary search can be used to search for a record on its ordering field value, and we know the complexity of the binary search. A binary search requires reading and searching a log2 base of the file blocks. All right, if we have b number of blocks, this is going to require log2 base b on the average, and it is a huge improvement over the linear search. So reading the records in order is quite efficient because the records are already ordered. So a ordered file looks like that. So each of the ordered files, the records are ordered in according to a ordering field. For example, here the ordering field is name, and you can see the ordered files, the records are ordered based on the ordering field of name. All right, so just want to remind you that the records will be stored in a block. Okay, records will be stored in the block. So for example, like here I have one block 1, here I have couple of records, block 2 will have couple of records. Okay, and the number of records in each block, I mean the number of record that we can store in each block depends on the size of the record and the size of the block, and this is known as blocking factor. Okay, so this following table shows us the average access time to access a specific record for a given type of file. So if the file is unordered or heap, so in that case I can do a sequential scan or linear search. So average block access will be b by 2. So here b is the number of blocks. Okay, so number of blocks to store all the records. Okay, so if I have a B block, okay, so in that case on average I may have to actually scan B by 2 record. I may have to access B by 2 record for sequential scan in the unordered file. Okay, so just to remind you again, to access a record we are going to actually access a block, the whole block, from the secondary storage to the main memory. All right, so that's why the efficiency in the database management system, they are going to be measured as a number of block. All right, so in the ordered file we can implement both sequential scan and binary search. So if we implement sequential scan, so the complexity will be B by 2 on average, but in the binary search we can implement we can implement binary search and the complexity will be log 2 base B. And we know that log 2 base B is a huge improvement, okay, a huge improvement over the linear scan or the sequential scan. In the hashed file, the record will be stored using the data structure hashing. So hashing for this file, it is known as external hashing. So the file blocks will be divided into m equal sized bucket. Okay, so m equal sized bucket. So each of the bucket will have a name like bucket 0, bucket 1, bucket 2. Okay, so typically each of the bucket will corresponds to one disk block. So I can have like each of the bucket can corresponds to one disk block. All right, so one of the file field will be designated to be the hash key of the file. Okay, and the record with the hash key value k will be stored in the bucket I. Okay, and we can find the value I as a hash function using a hash function with the key value. All right, so h is the hash function and k is our hash key. Okay, so we know, like we're familiar with the hashing technique. We know the searching is very efficient in the hash key, very efficient with the hash data structure. Okay, so without collision, the searching the searching takes actually order of 1 runtime. So it takes actually a constant runtime. Okay, but it can have a collision. A hashed file can have collision when a new record hashes to a bucket that is already full. Okay, so when I'm going to insert a new record in the bucket which is already full, that is going to create a collision. Okay, so we have actually technique for the collision resolution. So an overflow file is kept for storing such record, and overflow record that hash to each bucket can be linked together. So there are numerous methods for collision resolution. These are open addressing, chaining, and multiple hashing. So open addressing means actually we are going to proceed from the occupied position specified by the hash address, and the program will check the subsequent position in order until an unused position is found. Okay, so let's see this. These are our bucket. Let's see this bucket is already full, but we are trying to actually insert a new record here. Okay, and this is full. Then using the open addressing, we are going to proceed from that occupied position to all subsequent position. Whenever we are going to find a open space, we are going to insert the new record in that space. Okay, all right, we are going to insert the new record in that space. Chaining is in the chaining technique we are going to have some various overflow location. All right, so what actually we are going to do, we are going to extend the array with a number of overflow position. So additionally we are going to have a pointer field. Okay, a pointer field that will be added to each record location. So chaining looks like that. So let's say this is a collision. Okay, we are trying to insert a new record C2. Okay, and but that's a collision. This is the actually address that will get from the hash function, but they are already have some value. So what actually we are going to do, we are going to have some overflow location. Okay, means if we cannot store this in this record, we are going to store in those overflow location, and each of the overflow location is going to be linked by using some pointer. Okay, now if I am trying to find this record, I am going to use the address here. If I do not find here, I am going to follow this pointer address, and I will keep searching for the record. Okay, so multiple hashing means the program will apply a second hash function if the first result is a collision. Okay, so means actually if I find a collision, I am going to implement a second hash function on my data value. Okay, so using the second hash function, I will find a separate address where I need to store that record, and I am going to implement that. So if the second hash function also creates another collision, I have to implement a third hash function. Okay, so that's how actually there are numerous methods we can implement for a collision resolution. So here is the example how a hashed files looks like. So you can see each of the bucket number, okay, and block address. So based on the block address, it is going to be stored in the matching bucket. Okay, so to reduce the overflow record, typically a hash file, the DBMS typically keep a hash file 70 to 80% full. Okay, means DBMS doesn't actually completely full the hash file. Instead of that, typically it keep like 70 to 80% full. So the hash function h should distribute the record uniformly. So I mean the collision, the nature of collision depends on what hash function we are using. So if we choose a hash function like carefully, we may actually make the distribute the record uniformly among the bucket. That will reduce the possibility of collision. Okay, so if we have a too much collision, this is going to actually increase the searching time. Okay, without any collision in the hash data structure, the searching complexity is constant time. Okay, but if we have a collision, in that case we have to actually do the searching based on the way, depending on the way how we are doing the collision resolution. Okay, so the main disadvantage of static external hashing is that in the static hashing we are going to have a fixed number of bucket. Okay, so with a fixed number of bucket, that is always a problem because the number of bucket is fixed. So there will be always the possibility of having collision. Okay, and ordered access on the hash key is quite inefficient because in the hash key, if we want to read the record in ordered way, we have to first sort the records, so it's not very efficient. So this is the way how we can handle the overflow of bucket by chaining. Alright, so you can see that at the end of each bucket there will be a record pointer. Okay, there will be a record pointer. So for example, here this is not pointing any overflow bucket, but this bucket one, after that's full, we are going to keep the record pointer is going to point a overflow bucket. Okay, so the next record 981, we are going to store them in overflow bucket. Okay, so that's the overflow bucket, and like when the bucket 2 is full, we actually store the record in this bucket, overflow bucket, but there is a record pointer which will point to from this one to this one. All right.